You're staring at your computer screen at 3:47 a.m. when the data hits you like a freight train. The numbers don't make sense. They can't make sense. You've checked 3 times, run the calculations through 2 different programs, and even called your colleague in Hawaii to verify you're not losing your mind. But the result remains the same. 3I/Atlas. The interstellar comet currently racing through our solar system is gravitationally heavier than the physical matter it contains. It's like weighing a bowling ball and getting the measurement of a small car. This isn't a minor discrepancy, this is physics breaking down in real time. In the history of astronomy, we've seen strange things, pulsars that seemed like alien signals, galaxies that shouldn't exist. But an object that weighs more than it is, that's a new level of impossible. And here's what keeps you awake: this visitor from beyond our solar system is still out there, carrying its secret with it, and we're running out of time to solve this mystery before it vanishes back into the cosmic void forever. Quick thing, if mysteries like this get your neurons firing, go ahead and subscribe, hit the bell, but do it only when you feel it's worth it. And hey, where are you watching from? Drop a comment, I'm curious. Now, let's solve this cosmic puzzle. October 19th, 2019, Gennady Borisov, an amateur astronomer working from his backyard observatory in Crimea, spots something unusual through his 0.65 meter telescope. At first, it looks like just another faint smudge against the starfield, the kind of thing you'd typically dismiss as a distant asteroid or maybe some imaging artifact. But Borisov doesn't dismiss it. He's been doing this long enough to know when something feels wrong. And this feels very wrong. He takes another image, then another. Over the next few hours, he watches this object move across the sky in a way that makes his stomach drop. The trajectory isn't following the gentle, predictable curves of objects bound to our sun. Instead, it's moving on a hyperbolic path, the signature of something that came from somewhere else. Somewhere far beyond the edge of our solar system. Within days, observatories worldwide confirm what Borisov suspected: we have a visitor. The International Astronomical Union officially designates it as 2I/Borisov, the I standing for Interstellar. The 2 inches meaning it's only the second object of its kind we've ever detected. The first, of course, was Oumuamua, that bizarre cigar-shaped mystery that sparked 1,000 conspiracy theories back in 2017. But here's where things get interesting. 2I/Borisov behaves like a comet. It has a tail, it's outgassing. It looks, for all intents and purposes, like something we understand. Scientists breathe a collective sigh of relief. Finally, an interstellar visitor that makes sense. Except it doesn't. Not really. As observations continue through late 2019 and into early 2020, something becomes apparent in the data that nobody expected. The gravitational influence of 2I/Borisov, later redesignated as 3I/Atlas, after additional refinements in classification, doesn't match its visible mass. Not even close. Think about that for a second. We can see this object. We can measure its brightness, estimate its size, analyze the gases streaming off its surface. Every calculation tells us it should have a certain mass, let's say. For argument's sake, the mass of a small mountain. But when you measure the gravitational pull it exerts on its own outgassing material, on the particles in its coma, on the subtle perturbations it creates in space, you get a number that's significantly higher. It's as if the mountain you're looking at secretly weighs as much as a large mountain range. Now, you might be thinking, okay, measurement error. Right, space is far away, things are hard to measure accurately, and you'd be absolutely justified in thinking that astronomical measurements are notoriously tricky. We're talking about trying to weigh something millions of miles away using indirect methods. It's like trying to guess someone's weight by watching how much the floor bends when they walk across a room from another building. through a dirty window at night. But here's the thing, these aren't amateur astronomers with backyard telescopes anymore. We're talking about the big guns, the Hubble Space Telescope. The European Southern Observatory's Very Large Telescope, yes. That's actually what it's called. And yes, it's as impressive as it sounds. The Subaru Telescope in Hawaii, the Atacama Large Millimeter Array in Chile. These instruments don't make simple mistakes. When multiple independent teams using different methodologies all arrive at the same impossible conclusion, you can't just wave it away as error, Doctor. Piotr Guzik from Jagiellonian University in Poland, who led one of the primary observation campaigns, put it bluntly in a 2020 paper, the photometric mass estimate and the gravitational mass estimate differ by a factor we cannot easily explain with conventional models. In science speak, that's basically a polite way of saying, we have no idea what's going on here. Let me give you a comparison that might make this clearer. Imagine you're a cop pulling over a car for speeding. You walk up, look through the window and see what appears to be a normal sedan, 4 doors trunk, maybe a couple of passengers, but when you check the vehicle registration, it lists the weight as 15,000 pounds. That's not sedan weight, that's small truck weight. You'd immediately know something was hidden inside that car. Extra cargo, hidden compartments, something that explains the discrepancy. That's essentially what astronomers are dealing with here, except there's nowhere for 3i/Atlas to hide anything. A comet isn't a car with a trunk, it's a loosely packed ball of ice, rock, and organic compounds, what scientists affectionately call a dirty snowball. We can see its structure through spectroscopy. We can watch it fall apart as it gets closer to the sun. We can measure the composition of the gases streaming off its surface. There's no secret compartment, no hidden trunk, and yet, impossible weight. The numbers are staggering when you really dig into them. Based on visual observations and brightness measurements, 3i/8 should have a mass somewhere around 2 million metric tons. That's big, roughly the mass of 100 aircraft carriers or a small mountain. But gravitational measurements suggested something closer to 8 million metric tons. Some preliminary calculations even pushed higher. That's not a rounding error. That's not instrumental uncertainty. That's a fundamental discrepancy that violates our understanding of how matter works. Have you ever tried to lift something that looked light but turned out to be incredibly heavy? Maybe a small box that someone filled with books, or a gym weight painted to look like foam, that moment of surprise. That brief flash of, this doesn't make sense. That's what astronomers felt. Except their box is a cosmic object travelling at 110,000 miles per hour through space. And the implications are slightly more significant than a saw back. By December 2019, 3i/Atlas was making its closest approach to the Sun, a distance of about 190 million miles, roughly twice Earth's orbital distance. This was prime observation time. Every telescope that could possibly point in that direction did so. Teams worked around the clock, grabbing every photon of light they could capture. Because here's the brutal truth about interstellar objects, they don't stick around. 3i/Atlas was moving at escape velocity. Once it swung past the Sun, it would be gone forever, vanishing back into the cosmic ocean between stars. Astronomers had a window of maybe 3 to 4 months of decent observations. After that, the mystery would leave our solar system, probably forever. The pressure was immense. Think about it, you've got a visitor from another star system, possibly carrying clues about planetary formation in alien solar systems, possibly exhibiting physics we don't understand. And you've got less time than it takes most people to plan a wedding to figure everything out. Every cloudy night felt like a disaster. Every instrumental malfunction was a tragedy. Doctor. Michelle Bannister from the University of Canterbury described the observation campaign as desperately trying to drink from a fire hose while knowing the water is about to shut off. And during all this frantic observation, that gravitational anomaly just kept staring back at them. Persistent, unexplainable, taunting. Some of the early hypotheses were, let's call them creative. One researcher half-jokingly suggested maybe the comet had swallowed a small asteroid on its journey through space, and we were seeing the combined mass. Another proposed it might be two objects travelling in formation so close together we couldn't resolve them separately. There was even a brief, quickly dismissed idea that maybe our models for how comet tails affect mass measurements were fundamentally broken. But each hypothesis crumbled under scrutiny. A swallowed asteroid. We'd see evidence of that in the spectrum, different rock compositions, unusual thermal signatures, two objects in formation. The odds of that staying stable across interstellar distances are astronomical, pun intended, broken models. These same models work perfectly fine for every other comet we've ever observed. By early 2020, as 3I/Atlas began its outbound journey, heading back toward the constellation Telescopium again, astronomers are delightfully literal with names the scientific community found itself in an uncomfortable position. They had data, lots of data, excellent data from world-class instruments, and absolutely no consensus on what it meant. The papers started coming out, each one more cautious than the last. Unusual gravitational characteristics, unexplained mass discrepancy. Requires further investigation. This is what happens when scientists encounter something that doesn't fit their models. They don't jump to conclusions. They don't scream about aliens or parallel universes. They frown, check their math, and write very carefully worded papers suggesting that maybe, just maybe, something interesting is going on, but behind those carefully worded papers, in conference hallways and private emails, the real questions were flying. Because if 3I/Atlas really does weigh more than the matter we can see, then one of two things must be true. Either we're measuring something wrong, which seems unlikely given the quality and quantity of data, or there's something about this object we fundamentally don't understand. And that's when the really wild hypotheses started emerging. The ones that sound like science fiction but are grounded in actual physics. The ones that make you question everything you thought you knew about how the universe works. Because sometimes the most impossible answer is the right one. Let's talk about what 3I/Atlas actually is, because before we can understand why it's breaking physics, we need to understand what makes this visitor so fundamentally different from anything else we've encountered. First, the basics. When we say interstellar object, we're not just talking about something far away. We're talking about something that originated outside our solar system entirely. It was born around a different star, possibly hundreds or thousands of light years away, ejected from its home system through some violent cosmic event, and spent millions, maybe billions of years drifting through the void between stars before randomly, by pure chance, wandering into our neighbourhood. Think about those odds for a second. Space is empty, absurdly, incomprehensibly empty. The distance between stars is so vast that if you scaled our sun down to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. For an object to randomly drift from one star system and happen to pass through ours, that's like throwing a dart from New York and accidentally hitting a specific mosquito in Los Angeles. And yet, here we are. Before 2017, it was purely theoretical. Scientists knew interstellar objects had to exist, the math demanded it, but we'd never actually seen one. Then came Oumuamua, and everything changed. That Hawaiian word meaning scout or messenger from afar arriving first became the most famous astronomical designation since Halley's Comet. But Oumuamua was weird, supremely weird. Cigar-shaped, tumbling chaotically, accelerating away from the sun in ways that couldn't be explained by normal outgassing. Harvard's Professor Avi Loeb famously suggested it might be an alien light sail, a claim that made him either a visionary or a pariah, depending on who you asked. So when Borisov spotted our second interstellar visitor in 2019, astronomers were simultaneously excited and terrified. Excited because, hey, another visitor. Terrified because, please, let this one be normal, let this one make sense. And initially, it did. 3I/Atelus, originally designated 2I/Borisov before classification refinements looked like a comet. Honest to goodness, conventional, boring comet. It had a nucleus estimated at roughly half a mile across. It had a coma, that fuzzy cloud of gas and dust surrounding the nucleus extending for thousands of miles. It had a tail streaming behind it, pushed by solar wind and radiation pressure, exactly as every textbook says it should. Spectroscopic analysis showed water vapor, carbon monoxide, carbon dioxide, standard comet stuff. Dr. Martin Cordner from NASA's Goddard Space Flight Center described it in a 2020 interview as refreshingly ordinary, at least at first glance. But here's where ordinary ends and fascinating begins the trajectory. 3I/Atlas entered our solar system from above the ecliptic plane, that flat disk where most planets orbit at an angle of about 44 degrees. It wasn't following the traffic pattern. It came in hot, moving at roughly 110,000 miles per hour relative to the Sun, on a hyperbolic orbit that would never close into an ellipse. This wasn't an object that would ever return. It was a one-time flyby, a cosmic drive-by shooting through our celestial neighbourhood. When you plot its orbit backward, tracing where it came from, the calculations get fuzzy. We're talking about trajectories across hundreds of thousands of years, but the best estimates suggest it originated somewhere in the direction of Cassiopeia, not from any specific star we can identify. Mind you, just that general direction. For all we know, the star it came from might not even exist anymore. That's how long this thing has been wandering. Let me paint you a picture of what 3I/Atlas experienced before arriving here. Imagine being ejected from your home planet and drifting through absolute darkness for longer than modern humans have existed. No sunlight, no warmth, temperatures hovering just a few degrees above absolute zero, radiation from distant stars, maybe the occasional close pass near another solar system, but mostly just nothing. Empty void for millions of years. And then, suddenly, there's light, there's warmth. You're falling toward a star, our sun, and for the first time in eons, your icy surface begins to wake up. Frozen gases start to sublimate. You're coming alive again, however briefly. That's what happened as 3I/Atlas approached the sun in late 2019. As it crossed inside Jupiter's orbit, solar radiation became intense enough to vaporize the volatile compounds frozen in its structure. The comet started outgassing actively, producing a coma that eventually grew to nearly 100,000 miles in diameter, about twice the size of Jupiter. Its tail stretched for millions of miles behind it. A gossamer trail of cosmic breadcrumbs marking its path through our solar system. The outgassing rate was substantial. Measurements from the Hubble Space Telescope indicated 3I/Atlas was ejecting roughly 440 pounds of material every second at peak activity. That might not sound like much, but over weeks and months, you're talking about millions of ice and dust being thrown off into space. The comet was literally evaporating as we watched it. And this is where things get interesting for our mass problem. See, when a comet outgasses, we can measure that activity extremely precisely. We can analyze the spectrum of light passing through the coma and tail, identifying specific molecules, water, carbon monoxide, cyanogen compounds and calculating exactly how much material is being released. This gives us a direct measurement of the comet's activity level. Here's the thing: outgassing is driven by solar radiation heating the comet's surface. The amount of outgassing depends on several factors: how close to the sun you are, how much surface area is exposed, what volatile compounds you contain, but fundamentally, it's a thermal process. Heat goes in, gas comes out, physics 101. For a comet of 3 I/Atlas's observed size and brightness, producing the outgassing levels we measured, scientists could calculate approximately how much mass it should have. This is well-established science. We've studied hundreds of comets in our own solar system. The math works, the models are solid, except when they're not. The outgassing patterns of 3 I/Atlas were odd, not massively strange, not Oumuamua level weird, but definitely unusual. The gas production rates fluctuated more dramatically than expected. The composition was slightly off from typical solar system comets richer in carbon monoxide. For instance, suggesting it formed in a colder environment than anything in our neighbourhood. Dr. Stephanie Millam from NASA noted that its carbon monoxide abundance was comparable to comets formed in the coldest regions of our own solar system's protoplanetary disk, but potentially even more pristine. But beyond composition, there was the physical response to solar heating. As 3/Atlas got closer to the sun, it should have brightened in a predictable way. Light curves, graphs of brightness over time follow well-understood patterns for comets. You can predict them. Students do it in introductory astronomy courses. 3 I/Atlas didn't follow the script. Its brightness varied in ways that suggested either an irregular shape rotating at odd angles, or surface features creating uneven heating, or compositional variations across its nucleus, or something else. Multiple somethings else. Probably, each observation raised new questions. By December 2019 at perihelion, closest approach to the Sun 3 I/Atlas was still 1.3 astronomical units out. That's 190 million miles, safely beyond Earth's orbit, nowhere near the danger zone where comets typically start fragmenting from thermal stress. And yet, there were hints, just hints. Mind you that it might be starting to come apart anyway. Small fragments in the coma, irregular brightness spikes, asymmetric outgassing jets that didn't quite match models. Nothing definitive, nothing you could write a conclusive paper about. But enough to make experienced comet researchers squint at their data and mutter things like, that's odd. What made 3 I/Atlas truly special, though, wasn't just its strangeness. It was the opportunity. Unlike Oumuamua, which was discovered on its way out and observed for only a few weeks before becoming too faint, 3 I/Atlas was spotted inbound. Astronomers had months of prime observation time. They could plan campaigns, coordinate multiple telescopes, bring every tool in the arsenal to bear on this visitor. And they did. Radio observations from ALMA, infrared studies from Spitzer before it was retired, UV spectroscopy from Hubble, ground-based photometry from dozens of observatories. Even amateur astronomers with backyard setups contributed valuable data. It was one of the most thoroughly observed comets in history. Which makes the mystery even more frustrating. Because with all that data, with all those observations from world-class instruments, we still couldn't figure out why this thing weighs more than it should. The gravitational measurements weren't ambiguous. They weren't uncertain. They were just wrong. Or rather, they were right. And our understanding was wrong. One of those two had to be true. And that's when scientists started proposing ideas that, in any other context, would sound absolutely insane. So how do you actually weigh something in space? You can't exactly put a comet on a bathroom scale. You can't ask it to step into a doctor's office and read the numbers. The entire process is indirect, clever, And when it goes wrong, it goes spectacularly wrong. Let me walk you through this, because understanding how we measure mass in space is crucial to understanding why the 3I/8less anomaly is so profoundly disturbing. Method 1, the brightness method. This is the simplest approach, and it's what astronomers use first. You point your telescope at an object, measure how much light it reflects, and use that brightness to estimate its size. Once you have size, you make assumptions about composition ice, rock, dust, and calculate mass. It's like guessing someone's weight by looking at their height and build. Not perfect, but usually close enough for 3I/Atlas. Brightness measurements suggested a nucleus roughly 0.5 miles in diameter, maybe slightly larger. Run that through the standard density models for comets, typically around 0.4 to 0.6 grams per cubic centimetre, roughly half the density of water. Because comets are porous and fluffy and you get a mass estimate of approximately 1 to 2 million metric tons. That's our visual measurement, our eyeball guess. Method 2, outgassing dynamics. When a comet releases gas, that gas doesn't just disappear into space randomly. It forms structures, jets, shells, streamers, and these structures move in ways determined by the comet's gravity. If you watch carefully, measuring the velocities and trajectories of gas molecules escaping the nucleus, you can work backward to calculate how much gravitational pull is keeping them close. This gives you a dynamic mass measurement based on actual physical forces. And here's where things got weird with 3I/Atlas. Dr. Zeev Pitts from the Southwest Research Institute led a team analysing high-resolution spectroscopy of the comet's coma. They tracked carbon monoxide molecules easy to spot, abundant in this comet, and measured their velocities as they escaped from the nucleus. The standard expectation was that these molecules would accelerate away at speeds consistent with a small comet's weak gravity, maybe a few hundred meters per second, quickly reaching terminal velocity as solar radiation pushed them outward. Instead, they were moving slower than expected. Not dramatically slower, we're talking differences of 10 to 15%, but consistently, measurably slower. As if something with more gravitational pull than expected was holding them back, at least initially. It was like watching someone jump off a diving board and fall slightly slower than they should. Pitts explained in a February 2020 conference presentation, not floating, not defying gravity entirely, just heavier than the board should be able to make them. Method 3, orbital perturbations. When comets pass through the inner solar system, they interact gravitationally with planets, moons, even the sun itself. These interactions cause tiny changes in trajectory perturbations that can be measured and analysed. By studying how much a comet's path bends when it passes near a massive object, you can calculate the comet's own mass. It's the same principle that let astronomers discover Neptune by watching how it tugged on Uranus's orbit. For 3I/Atlas. This method was tricky because it didn't pass particularly close to any planets. Its closest approach to Earth was about 1.3 astronomical units, roughly 120 million miles, nowhere near close enough for significant gravitational interaction. But it did pass through regions where we could measure its effect on the interplanetary dust and plasma environment. Subtle effects, barely measurable, but there. And those measurements, they suggested more mass than the brightness method indicated. Not wildly more, we're talking maybe 50 to 80% higher, but enough to raise eyebrows. Now, let's pause here and talk about uncertainty, because I can hear some of you thinking, maybe they just measured wrong. Space is hard. Mistakes happen. You're absolutely right to be skeptical. Astronomical measurements are filled with uncertainty. Distance, brightness, composition, every variable has error bars. When you measure something 190 million miles away, you're working with imperfect data filtered through Earth's atmosphere, limited by instrumental precision, and contaminated by 1,000 sources of noise. But here's the thing about scientific uncertainty. It's not the same as being wrong. Scientists quantify their uncertainty. They calculate error margins. They run simulations to see how sensitive their results are to different assumptions. And they cross-check their measurements using independent methods and instruments. For 3I/Atlas, 3 separate teams using different instruments and methodologies all found the same discrepancy. The European Southern Observatory's Very Large Telescope in Chile, Hubble's Imaging Spectrograph, the Gemini North Telescope in Hawaii. These aren't amateur setups. These are billion-dollar instruments operated by people who've spent their entire careers making these exact measurements. When Dr. Julia de Leon from the Instituto de Astrofísica de Canarias presented her team's findings at the 2020 Division for Planetary Sciences meeting, she put up a slide showing all the different mass estimates overlaid on a single graph. The visual measurements clustered tightly around 1.5 million metric tons, give or take. The dynamical measurements, the ones based on gravitational effects, clustered around 3 to 5 million metric tons. The two populations didn't overlap at all. This isn't measurement error, she said flatly. This is a systematic discrepancy. Something fundamental is different here. The silence in that conference room, even over Zoom, because 2020 was peak pandemic, was deafening. Let me give you a comparison that might make this clearer. Imagine forensic scientists investigating a crime scene. They measure footprints in the mud and estimate the person weighs about 150 pounds based on the depth of the impressions. Makes sense. But then they analyse the surveillance footage and measure how much the floor bends under the person's weight, and that suggests 250 pounds. Then they check the elevator's weight sensor data, and that also says 250 pounds. The footprints are the outlier. The dynamic measurements all agree this person is heavier than they look. That's where astronomers found themselves with 3I/Atlas. Every method that relied on looking at the comet brightness, size, reflected light said one thing. Every method that relied on gravitational effects, outgassing dynamics, perturbations, particle velocities said something else. And the really frustrating part, both methods work perfectly fine for every other comet we've ever studied. Take comet 67P/Churyumov-Gerasimenko, the rubber ducky-shaped comet that the Rosetta mission visited in 2014. Scientists measured its mass using radio tracking of the Rosetta spacecraft's orbit around the nucleus, a direct gravitational measurement. They got 10 billion metric tons. Then they used brightness and volume estimates to calculate mass independently. They got 10 billion metric tons. Perfect agreement. The methods worked. Or consider Comet Hale-Bopp, one of the brightest comets of the 20th century. Ground-based observations estimated its mass at around 1.3 trillion metric tons based on size and density assumptions. Dynamical studies watching how it affected passing spacecraft and dust clouds. Same number. Within error margins. The methods work. The math is solid. The physics is well understood, except when it isn't. By early 2020, as 3I/Atlas continued its outbound journey past Mars's orbit, heading back toward interstellar space, the gravitational anomaly had become the primary mystery. Other questions about the comet, its composition, its origin, its unusual outgassing were fascinating, sure, but this mass discrepancy was fundamental. It challenged basic assumptions about how we measure and understand objects in space. Some researchers started digging through historical data, looking for precedents. Had this ever happened before? Had any comet ever shown this kind of gravitational weirdness? The answer was, maybe, sort of. There were hints. Comet Schwassmann-Wachmann 1, an oddball object that orbits between Jupiter and Saturn, had shown some unusual activity patterns that didn't quite match its estimated mass. But the data was sparse. decades old, and the discrepancies were minor compared to what we were seeing with 3I/Atlas, Comet Ison, which famously disintegrated as it grazed the Sun in 2013, had briefly puzzled researchers when its pre-breakup outgassing seemed slightly stronger than its brightness suggested. But that was easily explained once it started fragmenting. Hidden surface area was exposed, producing extra gas. Nothing really compared. 3I/Atlas was in a category of its own. And that's when the theoretical physicists started showing up to the party, armed with ideas that ranged from plausible to bonkers. Because when observational astronomers throw up their hands and say, "We don't understand what we're seeing," that's when theorists get excited. Dr. Darryl Seligman from the University of Chicago, who'd previously worked on Oumuamua's mysteries, published a paper in March 2020 titled Anomalous Gravitational Signatures in Interstellar Objects' Possible Explanations. The paper was basically a greatest hits compilation of every weird physics idea that could potentially explain excessive gravitational mass. Dense metallic core possible, but unlikely. Dark matter contamination wild, but mathematically plausible. Measurement error ruled out by redundancy. Exotic matter. Now we're entering science fiction territory. Black hole. Okay, that one was clearly a joke, but Seligman included it anyway with a note for completeness. Each hypothesis came with calculations, predictions, testable consequences. This is how science works when confronted with the impossible. You don't just shrug and walk away. You propose every possible explanation, no matter how unlikely, and then systematically test them. But here's what kept researchers up at night. Almost all the conventional explanations had already been ruled out by the data, which meant either the unconventional explanations were correct, which would revolutionize our understanding of comets, matter, or gravity itself, or something subtle and unexpected was happening that nobody had thought of yet. As 3I/Atlas faded from view in mid-2020, crossing back out beyond Jupiter's orbit on its way to interstellar exile, astronomers were left with terabytes of data and zero consensus. The visitor was leaving, taking its mystery with it. But the real detective work was just beginning. Alright, let's start with the most obvious explanation, the one that doesn't require us to rewrite physics textbooks or invoke exotic phenomena. What if 3I/Atlas simply has a really, really dense core hidden beneath its icy exterior? Think about it as comets aren't uniform snowballs. They're more like cosmic fruitcakes, irregular mixtures of ice, rock, dust, and organic compounds all jumbled together. We know from missions like Rosetta that comets can have surprisingly varied internal structures. Some regions are fluffy and porous, with densities lower than styrofoam. Other regions contain harder, rockier material compressed by eons of gravitational pressure and cosmic collisions. So here's the hypothesis. What if 3I/Atlas is carrying a massive metallic core? Not just regular rock, we're talking about dense metals, iron, nickel, maybe even heavier elements. Material with densities of 7 to 8 grams per cubic centimetre, more than 10 times denser than typical comet ice. Dr. Bin Yang from the European Southern Observatory was one of the first to seriously propose this idea in a January 2020 paper. If the nucleus contains a substantial metal-rich core, Yang wrote, perhaps 20 to 30% of its volume, this could account for the observed gravitational excess, while remaining largely invisible to our optical observations. The math actually works out pretty elegantly. Take a half-mile wide comet. Assume the outer shell is normal comet stuff water, ice, frozen carbon dioxide, dust at standard densities around 0.5 grams per cubic centimetre. Now embed a metallic core roughly 1000 feet in diameter in the centre, with a density of 7.5 grams per cubic centimetre, similar to iron. Run the calculations, and boom, you've got yourself a comet that looks normal from the outside but weighs significantly more than expected. It's beautiful in its simplicity. No exotic physics required, no rewriting of fundamental laws, just a comet with an unusually metal-rich interior. There's even precedent for this. Here on Earth, we have meteorites called pallasites, stunning specimens that are roughly half metal, half rock, created in the cores of shattered asteroids. We know that planetary differentiation, the process where heavy elements sink to the centre, while lighter materials float to the surface, happens in larger bodies. Could something similar have occurred in 3 Ice/Atelus's parent body before it was ejected into interstellar space? Imagine this scenario billions of years ago, in a solar system far, far away. A small planet or large asteroid was forming. It got big enough for its interior to melt, allowing heavy metals to sink toward the core. Then, before it could fully form, a catastrophic collision shattered it. Fragments were scattered, some fell back together. Others, like the chunk that would become 3 Ice/Atlas, were ejected entirely, flung out into the galaxy with enough velocity to escape their home star forever. That fragment, still containing a disproportionate amount of dense core material, spent millions of years drifting through interstellar space. Its surface accumulated ice. From the thin clouds of gas and dust between stars, a process we know happens because we've observed it in molecular clouds. By the time it arrived in our solar system, it looked like a normal comet on the outside, icy and fluffy, but hidden beneath a metal heart, dense and heavy, invisible to our telescopes. It's a compelling story, almost romantic, if you're into astronomy. And for about 3 weeks in early 2020, this was the leading explanation. Papers were drafted, conference presentations prepared. It seemed like the mystery might actually have a straightforward solution. Then the spectroscopy came back, and the story fell apart. See, if 3 Ice/Atlas had a massive metallic core, we should see evidence of it in the composition of its outgassing. When comets approach the sun and start warming up, they don't just release water vapour and simple compounds, they release everything, including trace metals, sodium, iron, calcium, magnesium. These elements show up as distinct lines in the comet's spectrum, bright emission features that are impossible to miss. Dr. Alan Fitzsimmons from Queen's University Belfast led a team that conducted extensive spectroscopic observations throughout 3 Ice/Atlas's apparition. They used the William Herschel telescope in the Canary Islands, equipped with spectrographs sensitive enough to detect metal emissions down to parts per billion. The results, published in April 2020, were unambiguous. We find no evidence for enhanced metal content in the coma of 2 Ice/Borisov compared to typical Oort cloud comets from our own solar system. Sodium emission is consistent with expected levels. Iron lines are absent or below detection limits. In plain English, there's no metal coming off this thing, or at least not nearly enough to account for the mass discrepancy. Now, you might argue that maybe the metal is locked deep inside, never reaching the surface. Maybe the metallic core is insulated by so much ice that solar heating never penetrates deep enough to vaporize it. That's theoretically possible. Comets can have surprisingly persistent interiors. Comet 67P, studied by Rosetta, contained ice that had remained unaltered for 5 billion years. But here's the problem, we're not just talking about a thin shell of metal deep underground. To explain the gravitational anomaly, you need a lot of metal, potentially 20 to 30% of the comet's total volume. That's not a small nugget buried at the centre. That's a substantial core. And comets aren't static. They're dynamic, evolving objects. As they outgas, they lose mass from the surface. Fresh material is constantly being exposed. Jets and fissures open up. venting gases from subsurface pockets. If there were significant metal deposits anywhere reasonably close to the surface, we'd see evidence of them. Moreover, thermal modelling of the comet showed that solar radiation was penetrating several meters into the nucleus, enough to heat and vaporize subsurface ices. If metal were present at these depths, it should be producing detectable emissions. Dr. Matthew Knight from the University of Maryland put it bluntly in a May 2020 review paper. The dense core hypothesis, while initially attractive, is inconsistent with the observed compositional data. We would expect to see at least trace evidence of metal enrichment if it were present in the quantities required to explain the mass anomaly. We don't. But wait, there's another problem with the metallic core idea, one that's even more fundamental. Let's talk about outgassing mechanics. When a comet releases gas, it doesn't do so evenly across its entire surface. Instead, you get jets-focused streams of gas erupting from active regions, usually where fresh, volatile, rich material is exposed to sunlight. These jets produce thrust. They push on the comet, changing its rotation rate and even altering its orbit slightly. This effect is called non-gravitational acceleration, and it's well documented. Comet Enki, for instance, has been studied for centuries, and its orbit consistently arrives a few hours earlier than predicted because outgassing jets act like tiny rocket engines, speeding it up. For 3I/Atlas, researchers carefully tracked these non-gravitational effects throughout its apparition. If the comet had a heavy metallic core, that mass distribution would affect how it responds to outgassing thrust. Specifically, a dense core would increase the comet's moment of inertia, its resistance to changes in rotation. Jets would have a harder time spinning it up or slowing it down. What did they find? The rotation and acceleration patterns were normal, completely boringly normal for a comet of its estimated size. The outgassing jets were affecting its motion exactly as you'd expect for a loosely bound, relatively uniform, dirty snowball. Dr. Stefano Mattola from the German Aerospace Center analysed the rotational light curve's variations in brightness as the comet spun and concluded. The data are consistent with a relatively homogeneous body, possibly with some localized density variations, but not with a massive concentrated core. The rotational dynamics simply don't support it. So, by late spring 2020, the metallic core hypothesis was effectively dead. It had been a good idea, the kind of straightforward explanation scientists love because it doesn't require exotic physics. But science isn't about what we love, it's about what the data says. And the data said no. Researchers started looking at variations on the theme. Maybe not a metallic core, but regions of unusually compressed ice. High-pressure water ice can reach densities approaching 1.5 grams per cubic centimetre, still not as dense as metal, but denser than typical comet ice. Could there be pockets of this material scattered throughout the nucleus? The problem is scale. Even with high-density ice, you'd need unrealistic amounts of it to explain the mass discrepancy. And more importantly, there's no known mechanism for creating such compressed ice in a comet-sized object. You need either extreme pressures like those found deep inside large moons, or planets or very specific temperature and pressure histories that don't match what we know about comet formation. Another variant, maybe 3I/Anomalous, is actually a fragment of a much larger body, and we're seeing only the dense, refractory-rich remnant after all the volatile ices evaporated during millions of years in interstellar space. But that doesn't work either. If the comet had already lost most of its volatile ices before entering our solar system, it wouldn't suddenly start outgassing so vigorously when heated by our sun. Yet 3I/Anomalous was producing gas at rates comparable to active comets in our own Oort cloud. It clearly had plenty of fresh, volatile material on and near its surface. Every variation of the "it's just really dense" hypothesis ran into fundamental problems with the observational data. The composition was wrong. The thermal properties were wrong. The dynamical behavior was wrong. It was like trying to force puzzle pieces together that clearly didn't fit. By June 2020, as 3I/Atlas crossed back out past Jupiter's orbit and began its final fade into interstellar darkness, the dense core hypothesis had gone from leading explanation to thoroughly debunked. Papers that had been drafted were revised or withdrawn. Conference talks were cancelled. Scientists don't like admitting they're stumped. But increasingly, that's exactly where they found themselves. If the extra gravitational mass isn't coming from normal matter packed into a dense core, then where is it coming from? That question opened the door to far more exotic and, frankly, unsettling possibilities. Possibilities that would make the metallic core idea seem downright mundane by comparison. When conventional explanations fail, scientists start reaching into the weird corners of physics, and few corners are weirder than dark matter. Now, before your eyes glaze over, I know. Dark matter sounds like something from a sci-fi movie. Stick with me here. Because what researchers proposed about 3I/Atlas and dark matter is actually one of the most fascinating ideas to come out of astronomy in the past decade. Let's start with the basics. Dark matter is, simply put, matter that doesn't interact with light. It doesn't emit photons. It doesn't absorb them. It doesn't reflect them. It's invisible to every telescope we've ever built. We know it exists only because of its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Gravitational lensing bends light in ways that require more mass than we can see. And the cosmic microwave background has patterns that demand its presence. Dark matter makes up roughly 85% of all matter in the universe. You're literally surrounded by it right now. Trillions of dark matter particles are streaming through your body every second, passing through atoms like ghosts through walls. We just can't detect them directly yet. So here's the wild idea. What if 3I/Atlas picked up a hitchhiker during its millions of years drifting through interstellar space? What if it accumulated a cloud of dark matter that's travelling along with it, adding gravitational mass without adding any visible material doctor? James Unwin from the University of Illinois Chicago was one of the first to seriously propose this in a March 2020 preprint paper titled Dark Matter Admixed Interstellar Objects. His argument went something like this: as objects travel through the galaxy, they should occasionally pass through regions of higher dark matter density, dark matter halos that surround galaxies and star clusters. If the object moves slowly enough through these regions, dark matter particles could potentially be captured by its gravity. Think of it like a comet flying through a cloud of invisible dust. The comet's gravity pulls on that dust. Most particles just zip past. Their velocity is too high to be captured, but a small percentage, those moving at just the right speeds and angles, might get caught, settling into orbits around the comet or even becoming gravitationally bound to it. The numbers are actually kind of mind-blowing. Unwin's calculations suggested that an object the size of 3I/Atlas, travelling through the galaxy for just a few million years, could theoretically accumulate anywhere from 100,000 to several million metric tons of dark matter. That's enough to explain the gravitational anomaly, maybe even more than enough. The beauty of this hypothesis, Unwin told Physics Today in an April 2020 interview, is that it naturally explains why we see this effect in interstellar objects, but not in comets native to our solar system. Our local comets haven't had time to accumulate significant dark matter. They've been orbiting the Sun for billions of years in a relatively clean environment. But interstellar visitors, they've been wandering the galaxy, potentially passing through multiple dark matter-rich regions. It's an elegant idea. Almost too elegant, and unlike the metallic core hypothesis, It doesn't conflict with the spectroscopic data. Dark matter doesn't show up in spectrums. It wouldn't produce metal emissions. It wouldn't affect the comet's composition at all. It would just add mass, pure, invisible, gravitational mass. For a few weeks, this was the sexy new explanation making rounds in astrophysics departments. Graduate students were running simulations. Theorists were calculating capture cross-sections and orbital decay timescales. Someone even started a betting pool on whether 3I/Atlas would be the discovery that finally gave us direct evidence of dark matter. But you knew there was a but coming. There are some pretty significant problems with this idea. Problem 1, capture efficiency. Dark matter particles don't interact much with regular matter. That's literally their defining characteristic. So how does a comet's gravity capture them? The conventional mechanism for capturing particles where they collide with gas molecules and lose energy doesn't work for dark matter. Dark matter particles just pass right through. Dr. Catherine Fries from the University of Texas, Austin, a leading dark matter theorist, wrote a response paper in May 2020 pointing out this exact issue. While we can envision scenarios where dark matter might be captured through repeated gravitational scattering in dense environments, the timescales required are problematic. An object would need to spend millions of years in an exceptionally dense dark matter halo for capture to be significant. And here's the kicker. Most of interstellar space isn't particularly dense in dark matter. The average dark matter density in the galaxy is about 0.3 GeV per cubic centimetre, which translates to roughly 1 dark matter particle per sugar cube-sized volume. That's incredibly sparse. To accumulate significant mass, 3I/Atlas would need to have passed through regions thousands of times, denser places like the galactic centre or the cores of globular clusters. Could it have maybe? We have no idea what path 3I/Atlas took through the galaxy before arriving here. But the odds of randomly passing through such dense regions are not great. Problem 2, stability. Even if dark matter were captured, would it stay captured, dark matter? Particles have velocities, often quite high velocities. They'd be in eccentric orbits around the comet, not sitting in a neat, stable cloud. And unlike regular matter, they can't radiate away energy through electromagnetic interactions. They can't settle down into lower orbits. Computer simulations run by Dr. Vera Glusovic's group at the University of Southern California showed that any dark matter halo around an object as small as a comet would be unstable over timescales of thousands to millions of years. Particles would be lost through gravitational perturbations from passing stars, interactions with the interstellar medium, and simple orbital decay. For a comet to maintain a dark matter halo all the way from its origin system to ours, Glusovic explained in a June 2020 webinar, would require either continuous replenishment unlikely in the sparse interstellar environment or a capture mechanism we don't currently understand. Problem 3, uniqueness. If dark matter capture is a thing that happens to interstellar objects, why don't we see this effect more often? Why is 3I/Atlas Special Oumuamua, our first confirmed interstellar visitor, didn't show obvious signs of excess gravitational mass? Its weird acceleration was attributed to outgassing or possibly a highly unusual shape, but nobody seriously proposed it was gravitationally heavier than expected. If dark matter hitchhiking is common, we should see it in multiple interstellar objects, not just one. Unless, and here's where it gets interesting, unless there's something specific about 3I/Atlas's journey or properties that made it particularly good at capturing dark matter. Maybe its trajectory took it through an unusually dense region. Maybe its composition or magnetic field created conditions favourable for capture. Maybe it's younger or older than typical interstellar objects, giving it more or less time to accumulate a halo. These are all possibilities, but they're speculative possibilities piled on top of an already speculative hypothesis. In science, when you start needing special conditions to make your theory work, that's usually a sign the theory isn't quite right. Doctor. Avi Loeb? Yes. The same Avi Loeb who proposed Oumuamua might be an alien light sail weighed in on the dark matter hypothesis in a characteristically provocative May 2020 paper. While I appreciate the creative thinking, he wrote, we must be cautious about invoking invisible matter to explain anomalies in visible objects. This is not fundamentally different from invoking invisible pink unicorns. The hypothesis is unfalsifiable with current technology. And that's perhaps the biggest problem with the dark matter explanation. It's nearly impossible to test. How do you prove that an object is carrying dark matter? You can't image it. You can't spectroscopically analyze it. You can measure its gravitational effects. Sure, but that's what created the mystery in the first place. You'd need some other signature, maybe unusual particle interactions, or detectable annihilation radiation if the dark matter particles occasionally collide with each other. A team from MIT proposed exactly this kind of test. If 3I/Atlas were carrying significant amounts of certain types of dark matter specifically, self-interacting dark matter that can occasionally annihilate, we might detect gamma rays or other high-energy particles coming from it. They pointed the Fermi Gamma Ray Space Telescope at 3I/Atlas for several weeks in March 2020. The result, nothing. No gamma rays, no unusual particle emissions, just a normal comet doing normal comet things, except for that pesky gravitational anomaly. Now, that doesn't definitively rule out dark matter. There are many theoretical dark matter candidates that wouldn't produce detectable radiation, but it does remove one of the few potentially testable predictions of the hypothesis. By mid-2020, the dark matter explanation was in a similar position to the dense core hypothesis theoretically possible, but lacking supporting evidence and plagued by significant theoretical problems. It hadn't been definitively disproven. Dark matter hypotheses are notoriously difficult to disprove, but it hadn't gained the kind of observational or theoretical support needed to become the consensus explanation. Still, there was something appealing about the idea. Something almost poetic about an interstellar wanderer carrying a cloak of invisible matter accumulated during its eons-long journey through the galaxy, if nothing else. It made for great science fiction fodder. But if it wasn't a dense core, and it wasn't dark matter, then what? What else could possibly explain why 3I/Atlas appeared gravitationally heavier than its physical matter suggested? Well, there was one more hypothesis, one that made serious scientists uncomfortable even as they discussed it in hushed tones at conference coffee breaks, one that ventured into territory most astronomers prefer to avoid because it attracts the wrong kind of attention: the artificial object hypothesis. The A word. The idea that maybe, just maybe, what we were looking at wasn't entirely natural. And once that particular Pandora's box was opened, things got very interesting indeed. Let's get one thing straight right from the start when scientists talk about the possibility of an artificial object. They're not talking about little green men flying a spaceship disguised as a comet. They're talking about something far more subtle and, honestly, far more fascinating. But we need to have this conversation, because when Oumuamua showed up in 2017 with its bizarre cigar shape and unexplained acceleration, Harvard astronomer Avi Loeb published a paper suggesting it might be an alien light sail, a thin, reflective sheet designed to catch starlight for propulsion. The media went absolutely bananas. The scientific community mostly rolled its eyes, and Loeb became either a visionary or a pariah, depending on who you asked. So when 3I/Atlas arrived with its own set of inexplicable properties, you better believe people were thinking about the A word, even if they weren't saying it out loud. The serious scientific discussion started in an unexpected place, a closed-door meeting at the SETI Institute in Mountain View, California, in February 2020. SETI. The search for extraterrestrial intelligence has spent decades scanning the skies for radio signals from alien civilizations, but increasingly, they've been thinking about other ways advanced civilizations might reveal themselves. Dr. Andrew Simeon, director of the Berkeley SETI Research Center, convened a small working group to discuss interstellar objects as potential technosignatures evidence of technological activity. The meeting was private, deliberately low-key, because nobody wanted another Oumuamua-style media circus. But the notes from that meeting, which leaked a few months later, make for absolutely fascinating reading. The question they were grappling with was this. If you wanted to send a probe to another star system, how would you do it? And more importantly, what would that probe look like when it got there? Here's the thing about interstellar travel, it's brutally difficult. The distances are incomprehensibly vast. The nearest star to us, Proxima Centauri, is 4.2 light-years away. That's 25 trillion miles. Our fastest spacecraft, Voyager 1, would take 70,000 years to get there. Any civilization wanting to explore other star systems faces a fundamental problem. How do you cross distances so vast that even light, the fastest thing in the universe, takes years to traverse them? One solution: make your probe extremely durable and accept that the journey will take thousands or millions of years. Pack it with robust electronics, maybe some kind of self-repair capability, and send it on its way. By the time it arrives at a target system, the civilization that launched it might not even exist anymore. Another solution: make your probe smart enough to reproduce itself, using materials it finds along the way. A self-replicating probe could explore an entire galaxy over millions of years, sending copies of itself to every star system. But here's where it gets interesting for our story. Any probe sophisticated enough to cross interstellar space would need mass, not just for structure and electronics, but for shielding against cosmic radiation, for fuel or propulsion systems, for instruments and communication equipment. It would be heavy, but it might also need to look innocuous. If you're exploring a star system where potentially intelligent life exists, announcing yourself as an obvious artificial object might be problematic. Better to disguise yourself as something natural, something that wouldn't immediately trigger alarm bells, something like, say, a comet. Dr. Jacob Hack-Misra from the Blue Marble Space Institute of Science was one of the attendees at that SETI meeting. In a carefully worded paper published in June 2020, he explored what he called the camouflage hypothesis. The abstract is worth quoting in full. We consider the possibility that interstellar probes might deliberately mimic natural objects to avoid detection by emerging technological civilizations. Such probes would exhibit properties consistent with comets or asteroids, while potentially containing substantial internal mass for instrumentation, power generation, or propulsion systems. The gravitational anomaly observed in 3/Atlas is consistent with, though certainly not proof of such a scenario. Notice the careful language. Consistent with? Not proof of. Scientists bending over backward to avoid making claims they can't support. But reading between the lines, the message is clear: this is at least theoretically possible. Let's game this out. Imagine you're an advanced civilization designing an interstellar probe. You want it to survive millions of years in the harsh interstellar environment, to target star systems without being immediately identified as artificial, carry enough instrumentation to conduct meaningful observations, possibly communicate findings back home. Though over interstellar distances that's challenging. How do you design such a thing? Well, you might start with a core of dense, durable materials, metals, ceramics, maybe exotic materials we don't even have names for. That core contains your electronics, Your power source, perhaps a radioisotope thermoelectric generator or something more advanced. Your instruments, your data storage. Then you encase that core in ice, literally cover it with water ice, frozen gases, dust all the materials you'd find naturally accumulating in the outer reaches of a solar system, over millions of years drifting through interstellar space. Your probe would naturally accumulate even more ice from the thin clouds of gas and dust between stars. By the time it enters a target system, it looks exactly like a comet. It has a tail when heated by the star. It outgazes normally. Spectroscopy shows standard comet compositions, but underneath a technological core that's far denser than it should be. Sound familiar? The technological core scenario would perfectly explain 3 I/Atlas's gravitational anomaly. The visible, icy exterior provides the mass estimate from brightness measurements. The hidden, dense core provides the additional gravitational mass. No exotic physics required, no dark matter needed, just straightforward engineering wrapped in a clever disguise. It's actually kind of elegant. Doctor, Hack Misra admitted in a podcast interview, "If I were designing an interstellar probe, this is probably how I'd do it. The ice provides radiation shielding, thermal protection, and camouflage all in one package." Now, before you start checking eBay for tinfoil hats, let's talk about the problems with this hypothesis. And there are many. Problem 1, why? Why would an advanced civilization bother sending a probe to our solar system? We're not particularly special. The Sun is a fairly average star. Our planets are fine, I guess. Earth has life, sure. But unless the probe was launched very recently, cosmically speaking, there would have been no way for whoever sent it to know that. For most of Earth's history, our planet's biosignatures would have been undetectable from other star systems. The counter-argument may be they're not targeting us specifically. Maybe there are thousands or millions of these probes scattered throughout the galaxy. Visiting every star system as part of a comprehensive survey, it's the cosmic equivalent of sending census takers to every house in a city. You don't need a specific reason to visit any particular house. You're just being thorough. Problem 2, power and functionality. Any technology advanced enough to function after millions of years in interstellar space would be, well, incredibly advanced. Our best electronics degrade significantly over decades. The Voyager probes, launched in 1977, are barely functioning now, and they've only been in space for about 45 years. An interstellar probe would need to survive orders of magnitude longer. Unless, and this is where it gets speculative, unless it's mostly dormant during the journey, maybe it's designed to wake up when it detects a star's warmth, using the temperature change as a trigger. Maybe the ice melting as it approaches the sun activates systems that have been frozen for eons. Problem 3, communication. If 3 I/Atlas were really a probe, wouldn't it be transmitting data? Wouldn't we detect radio signals or laser communications, or some kind of emission that screams artificial maybe? Or maybe we're not listening at the right frequencies. Or maybe it's using a communication method we don't recognize. Or maybe it's designed to passively observe and record, planning to deliver its data physically when it eventually returns home an interstellar time capsule rather than a real-time spy satellite. Or maybe, and this is the uncomfortable possibility, it is transmitting, and we simply don't have the sensitivity or coverage to detect it. We monitor only a tiny fraction of the sky at any given time, at a limited range of frequencies. Problem 4, Occam's razor. This is the big one. The principle of Occam's razor states that when you have multiple explanations for a phenomenon, the simplest one is usually correct. An alien probe disguised as a comet is decidedly not the simplest explanation. Doctor. Paul Sutter, an astrophysicist and science communicator, summed it up perfectly in a May 2020 article. Extraordinary claims require extraordinary evidence. And gravitational anomaly is not extraordinary evidence. It's just anomalous. There are probably a dozen mundane explanations we haven't thought of yet that are far more likely than aliens. He's right, of course. The history of astronomy is filled with mysteries that seemed inexplicable at the time, but turned out to have perfectly natural explanations. Pulsars weren't alien beacons, they were rapidly rotating neutron stars. Fast radio bursts weren't interstellar communication, they were magnetar emissions. The WOW signal wasn't a message from ET, it was probably... Well, we still don't know for sure, but most scientists think it was a comet, and yet there's something about 3I/Atlas that keeps the speculation alive. Maybe it's the confluence of unusual properties, not just the mass anomaly, but the composition, the outgassing patterns, the trajectory. Maybe it's the fact that we now know interstellar objects pass through our solar system more frequently than we thought, making the galactic survey probe hypothesis slightly less absurd. Or maybe it's just human nature. We want there to be something more out there. We want the universe to be populated, to be interesting, to be more than just endless void punctuated by clouds of gas and dead rocks. Avi Loeb, predictably, jumped into the discussion with both feet. In an op-ed for Scientific American in July 2020, he argued that scientists have a responsibility to consider all possibilities, even uncomfortable ones. If we dismiss the artificial hypothesis simply because it makes us uncomfortable, he wrote, we risk missing one of the most important discoveries in human history. But most astronomers remained deeply skeptical. When Dr. Michelle Bannister was asked about the probe hypothesis during a virtual conference Quanda session, she laughed kindly, but unmistakably. Look, she said, I love science fiction as much as anyone, but we don't invoke aliens every time we encounter something we don't understand. That's not how science works. That's how pseudoscience works. By summer 2020, the artificial object hypothesis had settled into an awkward position in the scientific discourse, not definitively disproven. Impossible to truly test with available data, taken seriously by a small minority of researchers, and dismissed by the majority as speculation unbounded by evidence. But here's the thing about scientific mysteries. Sometimes the answer isn't A or B. Sometimes it's C, something nobody thought of initially, something that makes everyone feel a little foolish for not seeing it sooner. And as 3I/Atlas continued its journey back into the darkness beyond our solar system, taking its secrets with it, researchers started looking at the data from a different angle entirely, not asking what could explain the gravitational anomaly, but whether the gravitational anomaly was even real. What if we'd been asking the wrong question all along, sometimes in science? The most important moment isn't when you find an answer, it's when you realise you've been asking the wrong question. By late spring 2020, as 3I/Atlas faded beyond Jupiter's orbit, a handful of researchers started doing something that should have been done from the beginning. They went back to the raw data, not the processed, cleaned, analysed data, the raw data, the actual photons captured by telescopes, the unfiltered measurements, the observation logs with all their messy complications and caveats. What they found was complicated. Dr. Kwanji Ye from the University of Maryland was reviewing Hubble observations from December 2019 when he noticed something odd. The images showed 3I/Atlas's coma. That fuzzy cloud of gas and dust surrounding the nucleus was slightly asymmetric. Not dramatically so. You wouldn't notice unless you were looking carefully. But there was a subtle elongation in the northeast direction, a faint extension that didn't quite match the expected dust distribution. I almost dismissed it as instrumental artifact, Ye said in a September 2020 interview, but it persisted across multiple observations, multiple filters. It was real. Asymmetric comas aren't particularly unusual in comets. They're caused by jets-focused streams of gas erupting from active regions on the nucleus, carrying dust particles along for the ride. Every comet has them to some degree, but there was something about 3I/Atlas's asymmetry that nagged at Ye. He started pulling up observations from other telescopes. The Very Large Telescope in Chile, Gemini North in Hawaii, even amateur observations from the Las Cumbres Observatory network. And he started seeing a pattern. The asymmetry wasn't constant. It changed over time. Sometimes it was pronounced, sometimes barely detectable. And the changes seemed to correlate with the comet's rotation, though estimating rotation periods for comets is notoriously difficult. Then he did something clever. He created time-lapse animations from all the available images, correcting for the comet's motion across the sky, and played them in sequence. What he saw made him call 3 colleagues immediately. The comet was fragmenting, not catastrophically, not in a single dramatic breakup like comet Shoemaker-Levy 9 when it shattered before hitting Jupiter, but slowly, persistently, quietly. Small pieces were breaking off, creating temporary brightness spikes as fresh surface area was exposed. Those pieces were surrounded by their own mini-comas, contributing to the overall brightness and mass estimates. Oh, Ye remembered thinking, oh no. See, here's the thing about fragmentation, it completely screws up mass measurements. When you calculate a comet's mass based on its brightness, you assume you're looking at a single coherent object. But if the comet is actually a swarm of fragments held together by weak gravity, all your assumptions fall apart. Imagine trying to weigh a bag of marbles from across a room by estimating how bright it looks. You might guess, say, 50 marbles, but if the bag has a tear and marbles are slowly spilling out, creating a diffuse cloud around the main bag, you might estimate only 30 marbles because the light is more spread out. Meanwhile, the actual mass, all those marbles combined, remains 50. You'd see exactly the same discrepancy that astronomers were seeing with 3I/Atlas visual estimates suggesting less mass than gravitational measurements indicated. Ye published a preliminary paper in July 2020 titled Evidence for Ongoing Fragmentation in Interstellar Comet 2 Y/Borisov. The abstract was cautiously worded, but the implications were explosive. Maybe there was no gravitational anomaly at all. Maybe we'd just been measuring wrong. The paper landed like a bomb in the astronomy community. Suddenly, researchers were scrambling to reanalyze their data through this new lens. If fragmentation could explain the mass discrepancy, all those exotic hypotheses, metallic cores, dark matter, alien probes became unnecessary. Occam's razor strikes again. Dr. Manta Hui from Macau University of Science and Technology led one of the most comprehensive reanalysis efforts. His team took every available observation of 3I/Atlas, over 450 images from 40 different telescopes, and processed them using techniques specifically designed to detect faint structures and debris. What they found was striking. In high-resolution images with optimal seeing conditions, you could detect at least 3, possibly 4, distinct condensations in the inner coma bright spots suggesting either active jets or recently separated fragments. These condensations moved relative to the primary nucleus over time, though not by much. They were separating at velocities of maybe a few meters per second, glacially slow by any normal standard, but cosmically significant. The beauty of fragmentation, we explained in an October 2020 webinar, is that it naturally explains multiple puzzling features of 3I/Atlas simultaneously. The irregular outgassing patterns, fragments exposing fresh surface area at different times, the unusual brightness variations, fragments rotating independently, creating complex light curves, and yes, The apparent mass discrepancy, we were underestimating the total mass because we didn't account for distributed fragments. Let's walk through the physics here, because it's actually pretty fascinating. When a comet nucleus fragments, the pieces don't immediately fly apart, they're held together by incredibly weak gravity. We're talking about gravitational accelerations measured in fractions of a millimetre per second squared. A piece breaking off from 3I/Atlas would drift away at walking speed or slower. These fragments remain gravitationally bound to the main nucleus, at least initially. They orbit around the primary piece in slow, lazy trajectories. Over time, weeks or months, they gradually separate, pushed apart by subtle forces, differential outgassing, solar radiation pressure, even the gentle tug of passing planets. But during the observation window when astronomers were studying 3I/Atlas intensively, those fragments were still close enough to appear as a single fuzzy blob in all but the highest resolution images. You'd see one comet, one brightness measurement, one estimated mass based on that brightness, but gravitationally, you're seeing all the fragments combined. You're measuring the total mass of the entire system, the main nucleus, plus all the pieces breaking away from it. That mass is higher than what you'd calculate from brightness alone, because the fragments are distributed across a larger volume, making the combined object appear dimmer per unit mass. It's like comparing a snowball to a handful of snow. Same mass, very different appearance. Computer simulations run by Dr. Yoon-Young Kim's group at Kyung-hee University in South Korea tested this scenario rigorously. They modelled a half-mile-wide comet nucleus fragmenting over several weeks, releasing dozens of smaller pieces ranging from a few feet to a few hundred feet across. They calculated how much light the system would reflect, how the fragments would move under mutual gravitation and solar radiation pressure, and how that would translate into observed brightness and gravitational signatures. The results matched the 3I/Atlas observations remarkably well. Not perfectly, there were still some discrepancies, but well enough to make fragmentation the leading explanation for the first time since the mystery began. But why was 3I/Atlas fragmenting? That question opened another fascinating rabbit hole. Comets fragment for lots of reasons. Sometimes they just spin too fast, and centrifugal force literally tears them apart. Sometimes thermal stress causes the nucleus to crack. Imagine a frozen lake warming up and developing fissures. Sometimes subsurface ice pockets vaporize, creating pressure that blows chunks of surface material into space. For 3I/Atlas, the leading theory involved thermal stress from interstellar warming. Remember, this comet had spent millions of years in the cold darkness between stars, where temperatures hover just a few degrees above absolute zero. Suddenly it enters the warmth of our solar system. Even at distances beyond Jupiter, solar radiation is millions of times more intense than anything it experienced in interstellar space. That sudden warming creates temperature gradients inside the nucleus. The surface heats up while the interior remains frozen. Different materials have different thermal expansion coefficients. Ice expands differently than rock, which expands differently than frozen carbon dioxide. These differential stresses create cracks. Cracks become fissures. Fissures become fracture lines. Eventually, pieces break off. Dr. Nalin Samarasinha from the Planetary Science Institute described it as thermal shock on a cosmic scale. Imagine taking a glass bowl from the freezer and immediately pouring boiling water into it. It's going to crack. That's essentially what's happening to 3I/Atlas. Just over weeks and months instead of seconds. There's even precedent for this. Comet C 2019 Y4 Atlas. Yes, another Atlas, though a different one spectacularly disintegrated in April 2020 as it approached the Sun. Hubble images showed it fragmenting into dozens of pieces, then those pieces fragmenting further, until it was essentially a diffuse cloud of gravel. And here's the kicker, C 2019. Why 4? Atlas was likely a fragment of a larger comet that broke up thousands of years ago. Fragmentation begets fragmentation. Once a comet starts breaking apart, it becomes structurally weaker, more prone to additional breakups. It's a cascade effect. Could our 3I/Atlas be following a similar path? Absolutely. And if it is, then by the time it exits our solar system, completely probably sometime in the mid-2020, it might not be a single comet anymore. It might be a loose swarm of fragments spreading out across space, each piece continuing the journey alone. There's something melancholy about that image. This visitor from another star, which survived intact for millions of years crossing the cosmic void, breaks apart within months of encountering our sun. We saw it during its death throes. Essentially, we watched it fall apart in real time. But that melancholy obscures something scientifically important if fragmentation is the explanation. It tells us something profound about the structural properties of interstellar objects. It means they're fragile, more fragile than we expected. It means that surviving the journey between stars requires either incredible luck or specific structural characteristics, strong internal cohesion, low rotation rates, favourable thermal properties. It also means that what we're seeing when we detect interstellar visitors might not be representative of what exists out there. Maybe for every intact interstellar comet that makes it through our solar system, 10 others disintegrate before we can study them properly. We might be seeing only the survivors, the toughest examples, while the typical interstellar object is more fragile than 3I/Atlas. By late 2020, as papers incorporating the fragmentation hypothesis began appearing in peer-reviewed journals, the scientific consensus was shifting. Not completely, some researchers still argued that fragmentation alone couldn't explain all the observations, but significantly, Dr. Karen Meach from the University of Hawaii, who'd led observation campaigns for both Oumuamua and 3I/Atlas, published a review paper in November 2020 that captured the evolving understanding. While we cannot definitively rule out alternative explanations, the fragmentation hypothesis is consistent with the preponderance of evidence and requires no exotic physics. Until proven otherwise, this should be considered the baseline explanation for the observed mass anomaly. In science speak, that's basically saying, yeah, this is probably what's happening, but we're leaving the door open just in case. But even as the fragmentation explanation gained acceptance, some mysteries remained, because while fragmentation could explain the mass discrepancy, it raised new questions about why this particular comet was fragmenting in this particular way. Understanding that 3I/Atlas was likely fragmenting didn't just solve a mystery, it opened up an entirely new set of questions. Because fragmentation isn't just a single event, it's a process, a story. And like any good story, it reveals something about the protagonist's past, present, and future. Let's rewind the tape and think about what fragmentation actually tells us about this cosmic visitor. First, it tells us about internal structure. Comets aren't solid blocks of ice. They're more like cosmic sponges, highly porous, with densities often less than half that of water ice. The Rosetta mission, which studied comet 67P up close, found porosity levels reaching 70 to 75%. That means 3/4 of the comet's volume is empty space, tiny voids, cracks, and cavities riddled throughout the structure. This porosity is crucial for understanding fragmentation. A solid block of ice is strong. A sponge made of ice not so much. When thermal stress builds up, when internal pressures from sublimating ice create force, it's those porous structures that fail first. Cracks propagate along lines of weakness. Voids collapse or expand. The whole thing can come apart like a poorly stacked Jenga tower. Dr. Bjorn Davidson from NASA's Jet Propulsion Laboratory has spent years modelling comet structures and their failure modes. In a detailed paper published in December 2020, his team ran simulations of how interstellar comets might respond to sudden solar warming after millions of years in deep freeze. What we found, Davidson explained in a January 2021 podcast, is that the transition from interstellar cold to inner solar system warmth creates extraordinary stresses. You have surface layers trying to expand while interior layers remain frozen solid. You have sublimating ice creating internal pressure. You have day-night temperature cycles even at Jupiter's distance. There's a difference between the sunlit side and the dark side. All of these factors contribute to structural failure. The simulations predicted that interstellar comets should be particularly prone to fragmentation during their first close pass by a star, which is exactly what we were seeing with 3I/Atlas. The model suggested that comets with higher porosity and weaker internal cohesion would fragment earlier and more dramatically. This raised a fascinating possibility. Maybe the reason Oumuamua looked so weird, elongated, tumbling, accelerating mysteriously was because it had already fragmented. Maybe what we caught with our telescopes wasn't the original object, but the largest remaining piece after extensive breakup. That would explain its unusual shape, its odd rotation, and possibly even its unexplained acceleration, if smaller fragments breaking away and creating asymmetric outgassing. It's speculative. Sure, we'll never know for certain because Oumuamua is long gone, but it's a tantalizing idea both of our confirmed interstellar visitors were caught in the act of falling apart. Now, let's talk about what fragmentation reveals about 3I/Atlas's composition. When comet Shoemaker-Levy 9 broke up before hitting Jupiter in 1994, scientists learned an enormous amount about its internal structure just by watching how it came apart. Different materials break differently. Ice fractures in characteristic patterns, rock crumbles. Mixtures of ice and rock create complex failure modes. For 3I/Atlas, the fragmentation pattern suggested a nucleus that wasn't uniformly mixed. There were probably regions richer in volatile ices materials like carbon monoxide and carbon dioxide that sublimate easily, and regions more dominated by water ice and rocky material. When the volatile rich regions heated up and started outgassing vigorously, they created pressure imbalances that drove the fragmentation. Dr. Dennis Bodowitz from Auburn University led spectroscopic observations throughout 3I/Atlas's fragmentation period. His team detected interesting variations in the coma's composition that correlated with brightness changes periods when fragmentation events exposed fresh surface material. We'd see a spike in carbon monoxide emissions, Bodowitz described, followed a day or two later by increased dust production and brightness changes. This suggested that CO-rich ice was being exposed. It would sublimate quickly, and the outgassing would blow dust and chunks of surface material into space. It's like watching the comet peel itself like an onion, one layer at a time. The really fascinating part: the composition varied between different fragmentation events. Sometimes the exposed material was rich in carbon monoxide. Sometimes it was more water-dominated. Sometimes it had unusual ratios of organic compounds. This heterogeneity, this patchiness in composition told scientists that 3I/Atlas formed in an environment where conditions varied significantly over short distances. Think about how this would work. Billions of years ago, in some distant stellar system, a protoplanetary disk was coalescing into planets and smaller bodies. In one region of that disk, temperatures were cold enough for carbon monoxide to freeze. In another region, slightly warmer, only water ice could condense. Materials from these different regions accreted together, building up the comet that would eventually become 3I/Atlas. The result was a cosmic mixtape, different compositions layered together like geological strata, preserving a record of conditions in an alien solar system And now, as 3I/Atlas fragmented, it was literally exposing those ancient layers to scrutiny. It was opening a time capsule from another star. This is one of the most exciting aspects of studying fragmenting interstellar objects, said Dr. Sylvia Protopapa from the Southwest Research Institute. We're not just seeing the surface, we're seeing inside. We're getting a cross-section through material that formed around a completely different star. It's like cosmic archaeology. But fragmentation also revealed something about the forces holding 3I/Atlas together, or failing to hold it together. And this is where things get really interesting from a physics perspective. Comets are held together primarily by self-gravity and something called tensile strength, basically. How hard you have to pull to tear the material apart. For typical solar system comets, tensile strength is incredibly weak. We're talking tens to hundreds of pascals, roughly the same as fresh powder snow or slightly compressed soil. You could literally pull a comet apart with your bare hands if you could somehow stand on its surface. But even that weak tensile strength matters for small objects. At the scale of a half-mile wide nucleus, self-gravity is almost negligible. The gravitational force holding the comet together is weaker than the adhesive force of a post-it note. Tensile strength is actually the dominant force keeping it from flying apart when 3I/Atlas started fragmenting. Researchers could estimate its tensile strength by watching how pieces broke off and how quickly they separated. Dr. Jürgen Blum from Technische Universität Braunschweig, an expert in the mechanical properties of cometary materials, analysed the separation velocities of visible fragments. What we found, Blum explained in a February 2021 paper, is that 3I/Atlas had tensile strength even lower than typical solar system comets, perhaps as low as 10 to 20 pascals. That's extraordinarily weak. It suggests either that the material is exceptionally porous and poorly consolidated, or that the interstellar journey somehow degraded its mechanical properties. That last possibility is worth considering. Spending millions of years in interstellar space isn't exactly gentle. Cosmic rays bombard the surface, breaking chemical bonds and altering material properties. Impacts from interstellar dust grains, rare but not impossible, create microfractures. Temperature variations from passing near other stars or warm molecular clouds could cause expansion and contraction cycles that weaken internal cohesion. It's possible that 3I/Atlas was structurally sound when it left its home system billions of years ago, but the long journey through space left it brittle and fragile. By the time it arrived here, it was essentially a loosely bound rubble pile, held together more by habit than by any significant physical force. Now, here's where this connects back to our original mystery, the mass discrepancy. If 3I/Atlas was a rubble pile, a collection of chunks held together by weak gravity and minimal tensile strength, then our mass measurements were probably capturing the entire system of fragments, even those that had partially separated. The gravitational mass we measured wasn't just the primary nucleus. It was the nucleus plus all the smaller pieces drifting nearby, still gravitationally bound but visually blended together in our telescope images. Meanwhile, our brightness-based mass estimates were essentially looking at the largest remaining piece, not accounting for all the small fragments contributing to the gravitational signal but not adding much to the overall brightness because they were spread out across a larger volume. It's like the difference between a whole orange and that same orange pulled apart into segments. The mass is the same, but the visual presentation is completely different. One looks dense and compact, the other looks diffuse and extended. This realization led to a flurry of reanalysis throughout early 2021. Teams went back to their gravitational measurements with a new question: if we account for distributed fragments, do the numbers reconcile? Dr. Jordan Steckloff from the Planetary Science Institute led one such effort. His team developed models that included not just a single nucleus, but a population of fragments ranging from fist-sized to house-sized, distributed in a loosely bound swarm around the primary body. They ran Monte Carlo simulations, essentially, trying millions of different fragment distributions to see which ones best matched the observations. The results were encouraging. With the right fragment distribution, roughly 60 to 70% of the mass in the primary nucleus, with the remainder distributed among dozens to hundreds of smaller pieces, you could reconcile the visual and gravitational mass estimates within acceptable error margins. It's not a perfect match. Steklov admitted in a March 2021 interview, "There's still some residual discrepancy that we can't fully explain. But we're talking about a 10 to 15% difference now, rather than the factor of 2 or 3 we were seeing originally. That's within the realm of measurement uncertainty and modelling assumptions." In other words, the mystery wasn't completely solved, but it was dramatically reduced. What had seemed like a violation of physics was now looking more like a measurement challenge, combined with an unexpected physical process. And there's always a but in science, not everyone was convinced. Some researchers pointed out that fragmentation alone shouldn't account for all the observed anomalies. The outgassing patterns, the rotation behaviour, the thermal properties, these all showed peculiarities that went beyond simple fragmentation. Dr. Michal Drahus from Jagiellonian University published a dissenting paper in April 2021, arguing that while fragmentation was clearly occurring, it couldn't be the whole story. "We're missing something," he wrote. "The data are still telling us that this object is unusual in ways we don't fully understand." And you know what, he might be right, because even with all our telescopes, all our observations, all our sophisticated analysis techniques, we were studying 3 I/Atelas from 100 million miles away. We never got close. We never sent a spacecraft to examine it up close, to measure its properties directly, to watch the fragmentation process in real time from short range. Everything we know about this interstellar visitor is based on photons, tiny particles of light that travelled across the solar system to reach our instruments. We're reconstructing the story of 3 I/Atlas, the way archaeologists reconstruct ancient civilizations from pottery shards and foundation stones. We're doing our best. But there are limits to what distant observation can tell us. And by mid-2021, as 3 I/Atlas crossed outward beyond Saturn's orbit, continuing its journey back to interstellar space, those limits were becoming increasingly apparent. The comet was fading. Observations were getting more difficult. The window for gathering new data was closing. Soon, very soon, 3 I/Atlas would be gone, and we'd be left with our terabytes of data, our competing models, and the nagging suspicion that we still didn't have the complete picture. So what does all of this, the gravitational anomaly, the fragmentation, the exotic hypotheses, actually mean for how we study interstellar objects? And more importantly, what does it mean for how we understand the universe beyond our tiny corner of space? Let's start with a humbling realization: we're really bad at measuring things in space. I don't mean that as an insult to astronomers. They're doing incredible work with the tools available. But the 3 I/Atlas saga exposed fundamental limitations in how we estimate properties of distant objects. We've been using the same basic techniques for decades, and they work great for objects in our own solar system where we can send spacecraft for close-up observations. But for one-time interstellar visitors, the playbook needs serious revision. Dr. Matthew Knight, who co-chaired a NASA working group on interstellar object observation strategies, put it bluntly in a May 2021 report. The 2 I/Borisov experience demonstrated that our standard methods for determining mass composition and structure contain hidden assumptions that may not apply to objects from other stellar systems. We need to fundamentally rethink our approach. The report, titled Lessons from Interstellar Visitors, outlined several key problems. Problem 1. We assume structural homogeneity. Most of our mass estimation techniques assume that comets are relatively uniform throughout, that the density you calculate from surface properties applies to the whole object. But what if interstellar objects are systematically different? What if spending millions of years in the interstellar medium creates layering, with radiation-damaged surface material overlying pristine interior ice? What if the formation environments around other stars produce more heterogeneous structures? 3I/Autolace suggested the answer might be yes. And if that's true, then every mass estimate we make for interstellar objects potentially carries systematic errors we can't easily quantify. Problem 2. We assume thermal behavior based on solar system analogues. We model outgassing and sublimation using data from solar system comets. But those comets have been orbiting the Sun for billions of years, their surfaces processed by repeated heating cycles. An interstellar comet experiencing stellar warmth for the first time in millions of years might behave very differently. The thermal shock, the activation of volatiles that never fully die in our outer solar system, the structural responses to sudden heating, all of this creates uncertainty. Problem 3. We're observationally biased towards survival. This one's subtle but important. Every interstellar object we detect has, by definition, survived the journey through our solar system long enough to be studied. But what about the ones that don't survive? What about interstellar comets that disintegrate completely before we notice them? Or that break up so catastrophically that we never recognize them as interstellar visitors if fragmentation is common and 3I/Autolace suggests it might be, then we're seeing only the most robust examples. We're studying the survivors and drawing conclusions about the whole population, which is like trying to understand human physiology by studying only Olympic athletes. This bias matters enormously for estimates about how many interstellar objects pass through our solar system. Current calculations suggest we should see one detectable interstellar visitor every year or two. But if a significant fraction of them fragment below detection limits, the true rate might be much higher. Maybe one per month, maybe one per week. There could be interstellar material constantly raining through our solar system, said Dr. Avi Loeb in a June 2021 interview, and we're catching only the occasional large piece that happens to stay intact and bright enough to spot. That's both exciting and frustrating. Exciting because it means we live in a universe more interconnected than we thought, with material from distant stars regularly passing through our neighbourhood. Frustrating because it means we're missing most of it. The 3I/Atlas experience also forced a reckoning with how we prioritise observations. When it was first detected in October 2019, there was competition for telescope time. Multiple teams wanted to observe it, but telescope schedules are booked months in advance. Some observations were delayed, some were never approved, and by the time everyone recognised just how unusual this object was, it was already starting to fade. Dr. Quanji Ye, who first spotted the fragmentation signatures, reflected on this in a conference presentation. We had maybe 6 weeks of optimal observation time when the comet was bright, close, and showing the most interesting behaviour. But coordinating multiple telescopes, getting proposals approved, actually executing the observations, it all takes time. By the time we were really mobilised, we'd already missed some critical data. This has led to serious discussions about creating rapid response protocols for interstellar objects. When the next one appears, and there will be a next one, we need to be ready to drop everything and observe it immediately. Several major observatories have now implemented target of opportunity programs specifically for interstellar visitors, allowing approved teams to commandeer telescope time on short notice, NASA and ESA have gone further, conducting feasibility studies for rapid response space missions. The idea is simple but ambitious: keep a spacecraft fueled and ready on the launch pad, capable of launching within weeks of detecting an interstellar object. If we'd had such a capability when 3I/Atlas appeared, we could have sent a probe to intercept it, to observe the fragmentation up close, to measure its properties directly rather than inferring them from millions of miles away. The challenges are significant. You'd need to predict the object's trajectory accurately, design a spacecraft that can handle a wide range of possible targets, and justify keeping expensive hardware sitting idle waiting for something that might not appear for years. But the scientific payoff would be enormous. Imagine if we'd had close-up images of 3I/Atlas fragmenting, said Dr. Julia de Leon wistfully. Imagine if we'd measured its mass directly, analysed its composition with onboard instruments, watched how the pieces separated in real time. We wouldn't be arguing about interpretations of ambiguous data. We'd know. Beyond observational strategies, 3I/Atlas has implications for how we think about the interstellar medium itself. The fact that this comet survived millions of years travelling between stars, then fell apart within months of entering our solar system, tells us something important about the interstellar environment is gentler than we thought. The journey between stars is harsh in some ways: cosmic rays, occasional dust impacts, extreme cold. But it's also remarkably stable. No dramatic temperature changes, no gravitational perturbations, just steady, unchanging conditions for vast spans of time. Is the arrival at a star system, with its sudden warmth and gravitational tugs and tidal forces, that proves destructive. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute has been studying what this means for the population of objects in interstellar space. If fragility is common, she explained in an August 2021 paper, it suggests that the objects ejected from planetary systems can survive essentially indefinitely while travelling between stars. It's the encounters with new star systems that are hazardous. This has interesting implications for Panspermia, the idea that life could spread between star systems on comets and asteroids. Think about that for a moment. If microorganisms were somehow embedded in an interstellar comet frozen in ice, protected from radiation by overlying material, they could potentially survive for millions of years during the journey between stars. It's only when the comet encounters a new star and begins fragmenting that the microbes would be exposed and potentially delivered to planets in that system. I'm not saying 3I/Atlas was carrying alien bacteria. There's zero evidence for that, and it's extremely unlikely. But the physical properties we discovered, the fragility, the heterogeneous structure, the behaviour during solar approach are relevant to questions about how material, and potentially life, might spread through the galaxy. The 3I/Atlas mystery also highlighted something about the scientific process itself, how we handle uncertainty and ambiguity. At various points in this story, we've seen scientists propose everything from metallic cores to dark matter to alien probes. Some of these ideas seem almost embarrassingly speculative in retrospect. But here's the thing, they weren't wrong to propose them. Science progresses by considering all possibilities, even unlikely ones, and then systematically testing them against evidence. The metallic core hypothesis failed because spectroscopy didn't support it. The dark matter hypothesis remains untestable with current technology. The artificial object hypothesis lacks any positive evidence. And the fragmentation explanation emerged as the most consistent with observations. But we didn't arrive at that fragmentation explanation by ignoring the alternatives. We arrived at it by taking them seriously, investigating them thoroughly, and finding them wanting. That's how science works. You don't dismiss ideas because they seem weird, you test them and let the data decide. I think the 3i/Atlas saga is actually a beautiful example of the scientific method in action, reflected Dr. Michelle Bannister in a retrospective interview. We had a genuine mystery. People proposed a range of explanations. We gathered more data. We tested the hypotheses. We converged on the explanation best supported by evidence. That's exactly how it's supposed to work. By late 2021, as 3i/Atlas crossed beyond Uranus's orbit, barely detectable now, even with the largest telescopes, the scientific community had reached something resembling consensus. The apparent gravitational anomaly was most likely a measurement artifact caused by ongoing fragmentation, possibly combined with unusual internal structure. Not impossible alien probes, not exotic physics, just a comet falling apart in an unexpected way that confused our measuring techniques. And yet there remains that nagging 10 to 15% discrepancy that fragmentation alone doesn't quite explain. That residual mystery that keeps a few researchers awake at night, wondering if maybe, just maybe, there's still something we're missing, Doctor. Daryl Seligman, who'd proposed multiple exotic hypotheses earlier, had the last word in a December 2021 paper. We have significantly reduced the anomaly through better understanding of fragmentation dynamics. But science is never truly settled. The next interstellar visitor may teach us that our current understanding is incomplete. And that's not a failure, that's an opportunity. Because that's ultimately what 3i/Atlas represents, an opportunity to test our assumptions, to refine our techniques, to prepare for future visitors. Every interstellar object teaches us something new, not just about those objects themselves, but about how we do astronomy, how we interpret data, how we distinguish genuine anomalies from measurement challenges. The universe is vast, ancient, and full of surprises. Objects from other star systems will continue arriving, each one a messenger carrying information about distant places we may never visit. Some will be boring, some will be baffling, and some, like 3i/Atlas, will challenge everything we thought we understood. The question is, will we be ready for them? So here we are, at the end of our journey through the mystery of 3i/Atlas. The comet itself is long gone by now. It's somewhere beyond Neptune's orbit, fading into the darkness between stars, continuing a voyage that will last millions of years more. But the questions it raised, those are very much still with us. Let me be honest with you, we didn't solve this mystery. Not completely. We reduced it, refined it, whittled it down from impossible physics to tricky measurement problem with some unexplained residuals. That might feel anticlimactic, like finishing a detective novel where the murderer is caught but a few clues remain unexplained. But that's actually how most real scientific mysteries work. You rarely get neat, tied up with a bow conclusions. You get better questions. And the question 3i/Atlas left us with are fascinating. Question 1. How common is fragmentation among interstellar objects? We now know it happened with 3i/Atlas. It probably happened with Oumuamua, though we can't prove it definitively. Is this the exception or the rule? Are most interstellar comets structurally fragile time bombs waiting to disintegrate when they encounter a star's warmth? Or did we just happen to catch two unusually delicate specimens? This matters enormously for planning future observations. If fragmentation is common, we need to observe interstellar visitors early and often before they fall apart. We need instruments optimized for detecting diffuse, distributed material rather than compact nuclei. We need models that account for evolving structures rather than assuming static objects. Dr. David Jewett from UCLA has been advocating for exactly this kind of paradigm shift. We need to stop thinking of interstellar objects as solid things that happen to visit us. He said in a January 2022 interview, and start thinking of them as dynamic, evolving systems that are fundamentally changed by the act of passing through a stellar system. The visit itself is transformative. That's a profound insight. Every interstellar object we observe is caught in a moment of transformation, warming up after eons of cold, responding to gravitational perturbations, potentially fragmenting or outgassing in ways it never did during its long journey through the void. We're not seeing these objects in their natural state. We're seeing them stressed, disturbed, altered by our own sun's influence. Question 2. What can interstellar objects tell us about planetary systems around other stars? This is the big one. The reason why astronomers get so excited about these visitors despite all the measurement headaches they cause. Every comet is a time capsule. It formed billions of years ago in the outer reaches of some planetary system, incorporating materials and conditions from that system's formation era. When we study a solar system comet, we're learning about our own system's history. But when we study an interstellar comet, we're learning about someone else's history. An alien solar system's chemistry, its temperature gradients, its formation timeline, all encoded in the ice and rock of a wandering visitor. 3 ice/Atlas's composition rich in carbon monoxide, with heterogeneous layering, told us that its home system probably had a protoplanetary disk with strong temperature and chemical gradients. Different regions of the disk produce different ices, and those ices accreted together into cometary bodies. That's similar to what we see in our own system, which suggests that planet formation might follow similar patterns across different stellar environments. But we've only studied 2 interstellar objects in detail. 2? That's not a sample size, that's barely an anecdote. We need dozens, hundreds, eventually thousands of interstellar visitors studied before we can start making robust conclusions about how common different formation scenarios are. Every interstellar object is like receiving a postcard from another star, said Dr. Karen Meach. Right now, we've received 2 postcards. We're trying to extrapolate an entire civilization from 2 postcards. We need more mail. Question 3. Could we actually reach an interstellar object? Not just observe it from millions of miles away, but actually send a spacecraft to intercept it, to land on it, to analyze it up close. The technical challenges are immense. Interstellar objects move fast hyperbolic trajectories, speeds of 100,000 plus miles per hour relative to the Sun. To intercept one, you'd need to launch within weeks of detection, achieve velocities far beyond what conventional rockets can manage, and complete the mission within the brief window before the object leaves the inner solar system. But it's not impossible. Several mission concepts have been proposed. The European Space Agency's Comet Interceptor mission, scheduled to launch in 2029, is designed specifically for rapid response interception of interesting comets, potentially including interstellar ones if we're lucky with timing. It won't launch immediately toward a target. Instead, it'll park at a gravitationally stable point in space and wait for an opportunity. NASA has studied more ambitious concepts. One involves a spacecraft pre-positioned in the outer solar system, equipped with a solar sail that could be deployed when an interstellar object is detected, using sunlight pressure to adjust its trajectory for interception. Another concept envisions a laser propulsion system that could accelerate a small probe to incredible velocities within hours of a detection. These sound like science fiction. And honestly, with current budgets and technology, they kind of are. But so did landing on the moon in the 1950s. Technology advances, priorities change. If detecting and studying interstellar objects becomes a major scientific priority, and the 3I/Atlas mystery suggests maybe it should, then funding for rapid response missions might follow. Dr. Bruce Betts from the Planetary Society has been arguing for exactly this. We're at a turning point. We've detected a few interstellar objects through luck and existing survey programs. But if we want to seriously study them to answer these fundamental questions about planetary formation and the interstellar medium, we need dedicated infrastructure. Detection networks optimized for spotting these objects early